You know, we're still doing this example problem. So we're still on this principal stress and principal coordinate system example. And the problem was we had a stress tensor that was pre-cooked to work out in a good way. But the idea is that this is just what was given. So our stress tensor is 8.83, 0, 3.21, 0, -5, 0, 3.21, 0, 1.17. And we want the principal stresses the corresponding coordinate system and the maximum shear stress. And what we've done so far is we already calculated the eigenvalues. We did that by setting that determinant. So we subtracted the lambdas along the main diagonal, took the determinant, set it equal to 0. That gave us a cubic polynomial. And so we already found that the principal stresses are 0, 10, and -5. And we also found that the axis, the outward facing normal for the face where the normal traction is 0, had components. So that was plus or minus 0.342, 0, -0.940. That's in the original coordinate system, by the way. So all of these are in the original coordinate system. Now we have 2 more axes to find. Well, actually, since we're looking for a coordinate system, it's enough to just do it one more time. And then if, say, you have 2 of the coordinate axes, you can find the third one just with a cross product. Okay, you don't have to go through the third eigenvector calculation. But so let's do it for 10 now. So everyone remember where we are in this problem? This all sort of makes sense. You kind of remember what we did? Okay, so now we're going to use lambda equals 10. And so we have this equation that says 8.83 minus 10, 0, 3.21, and then 0, -5 minus 10, 0, and then 3.21, 0, and 1.17 minus 10. That's what it was, right? Yes. And we're trying to find nx, ny, nz, where those are a unit vector. So we're going to specify that's a unit vector because even though this is 3 equations, remember, this happened on the last one, and it's going to happen anytime you do this, this is going to happen. Only two of those equations are independent. The third one is dependent on the other two. And so you can always specify one parameter. And so the way we're going to do it is by making this a unit vector. Okay. Okay, so when you do the subtraction, this matrix equation becomes negative 1.17, 0, 3.21, 0, negative 15, 0, 3.21, 0, negative 8.83. Nx, Ny, Nz is equal to 0. Okay, so since we're using lambda equals 10, and we put that into the equation, this is going to be the eigenvector that corresponds to lambda equals 10. Okay, so we're coming up with the axis, basically the outward facing normal for the face that has a traction of 10. Okay, a normal traction of 10. And our equations are negative 1.17 nx plus 3.21 nz is equal to 0. And then negative 15 ny is equal to 0. And then 3.21 nx minus 8.83 nz is equal to 0. Okay, well, the second of these two equations tells us that ny is 0 again. And these two are a linear, one is a linear multiple of the other one. So only one of these is useful. Let's specify nx is equal to 1. We'll just choose that arbitrarily. And we get negative 1.17 times 1 plus 3.21 nz is equal to 0. And so nz is 1.17 divided by 3.21. And what do you get for that? 0.3644. Okay. And so we have this, so now we have this eigenvector, but it's not a unit vector yet. So I'll just write it like this. And it is 1, 0, 0.3644. And now divide that by its magnitude. And you get a unit vector that I suppose is probably going to be 0.940, 0.342. Okay, so let's think about what we know now. So we have principal stresses of 0, 10, and negative 5. The 0 corresponds to 0.3420, negative 0.940, plus or minus. The 10 corresponds to plus or minus 0.940, 0.342. And We haven't done this one yet. We don't have to, but let's think about some of the possibilities here. So there are a few possibilities now for the principal stress tensor and the coordinate system that principal stress tensor is in. You know, the principal coordinate system. Okay, one is, let's say, the new x-axis is the old 0.342, 0, negative 0.94. Okay. And the new, this should say new, y-axis is 0.940, positive 0.342. You can check and see if those are perpendicular to each other with a dot product or something. Dot product between those needs to be 0. So now, what does that mean that the z-axis is? The coordinate system has to satisfy right-hand rule requirements. Okay, x cross y has to be equal to z. So you can just take the cross product of, so let me write it like this. You can take this new x-axis, cross it with the new y-axis, and that has to give you the new k-axis. Can someone take the cross product between those two? Oh, yeah. Yep. So those two, you can see, are both in the xz plane. So the only thing we'd be figuring out by taking the cross product is whether the right-hand rule says it has to be positive y direction or the negative y direction. You could also just plot that out and see which direction it would be, but that means that the new z-axis has to be 0, 1, 0. Okay. So in that coordinate system, our principal stress tensor, or just our stress tensor if we're in that coordinate system, has 0 in the x normal element, because that x-axis was the eigenvector for the 0. Positive 10 for the y, because our y-axis was the eigenvector for the 10. And then negative 5. And this is in megapascals. Yep. Take the cross product of the x and the y. Because the x-axis crossed with the y-axis has to be the z-axis. Yep.
So if you're doing this on the calculator and you do the eigenvector,
mm-hmm.
and you do like the N1,
yeah.
N2,
you can, so let me do a couple other, so we have all these choices, and there's really not any reason to choose one over the other one, but let's think of another possibility, okay? We could say Well, we could say that we want the x-axis to be, this is the one that's closest to the x-axis. Okay. So maybe we want to make that our new x-axis so we don't have to rotate them as much, So the new x-axis is 0.940 0 positive 0.342. Okay. So remember that one corresponds to, what did that one correspond to? That corresponded to our 10, right? Each one of these eigenvectors is linked to an eigenvalue. That's the one that we got by putting in a lambda value of 10. Okay. So this one is linked to the 10 in the first example. This one is linked to the 0. This one is linked to the -5. So now in this new example, this is the one that's linked to the 10. Yep. When you did the cross product? Okay. Okay. Yeah, we should. So, thank you. You can't use a coordinate system where the z-axis is not x cross y. So that would cause problems eventually. Okay, so now let's call this, since that is closest to our old x-axis, let's call this our new x-axis. But remember, this is still the eigenvector that's linked to the 10. Okay. And now the one that's closest to our y-axis is, so our new y-axis is our old y-axis. And just like it was before, that's still the one that's linked to the -5. Okay. Well, we already figured out that, so we know that this one, by taking that cross product, is going to be linked to 0, 1, 0, plus or minus. You can pick them at random, or you can have some reason to pick them the way you do, or you can do them in order. A lot of people do them in order from the maximum eigenvalue to the minimum eigenvalue. But no matter how you choose to order them, you just have to choose a coordinate system that satisfies x cross y is equal to z. Okay. So that's the new y-axis, and now x cross y has to be equal to z. If you took that cross product, you'd get back your new z-axis, which would be negative 0.3420, positive 0.940. And that one is linked to the 0 eigenvalue. And I don't know how many permutations there are, but you have several options. Okay. Yeah, it's totally arbitrary. In this one, what we would have is, since our new x-axis is linked to the 10, in this coordinate system, we have 10 in the x position, -5 in the y position, 0 in the z position. Okay. But let's think about what this means in terms of a stress cube, okay? So let's think of a stress cube. And we know that, well, let me draw it associated with this one. We know that for x, we have +10. For y, we have -5. And for z, we have 0, okay? Well, on the other coordinate system we chose, this was the positive x face, the one with 0. Right? And the one with 10 was the positive y face. So let's see. So this is x, this is y. Actually, this is x, this is y. That means positive z is underneath. Okay. X, y, x to y. Yeah. So what I'm trying to show here is this stress cube still works for the other principal stress, just the different faces have the different labels. Okay? So as a stress cube, it still tells the same story, even though you're choosing different faces to represent the different. Okay, so this can be x, y, z, or this can be x, y, z. Okay, but it all matches with our calculations. So choices of which axis is which don't matter. As long as the x-axis crossed with the y-axis is equal to the z-axis. Okay, so which choice do we want? Let's say that we went, and if you plug this into a calculator, so what my calculator gave was the values in order 10, 0, -5, and the corresponding axes were 0.940, 0.342, -0.342, 0.940, and 0.10. Okay, but that's just one of these permutations. Okay, so your calculator will give one of these acceptable permutations. They will give the eigenvalue order that matches the eigenvector order. Yes. Okay, so if you do those two commands, the first eigenvalue it gives you will match the first, it'll be linked to the first eigenvector it gives you, the second one, and so on. Okay. Okay, so let's say that so here's what I normally choose. In whatever order I calculated the eigenvalues, I just make those x, y, z. So let's go 0, 10, -5. Okay. So let's say this principal stress tensor is 0, 10, -5. Okay. And that corresponds to some coordinate system. It actually corresponds to two coordinate systems. Like say it corresponds to this coordinate system and the exact opposite of that with everything opposite. Yes, it should. Okay, so let's choose that one. So now we want to calculate the maximum shear stress. Okay. So the maximum shear stress is the maximum principal stress minus the minimum principal stress divided by 2. So that's 7.5. Okay. If you want to find the a stress tensor that has that value of shear stress, so if you want to find a stress tensor with a shear stress absolute value of 7.5, identify the axis corresponding to the middle eigenvalue, okay, so in our new coordinate system, which of these axes, x, y, or z, corresponds to the middle principal stress? X, yep, because that 0 is the middle of the 3. And then rotate the coordinate system plus or minus 45 degrees about that axis. So if we're going to rotate positive 45 degrees about that axis, our rotation matrix is 1, 0, 0. This is how you rotate about the x-axis. Cosine of 45, sine of 45, negative sine of 45, cosine of 45. Okay. And our new stress tensor that has the max shear stress value is going to be Q times our principal stress tensor times Q transpose. And if we do this, we should end up with a stress tensor that has a 7.5 in one of the shear spots. Okay, but we'll have the whole stress tensor. So let me just pause. And what you get is 0, 0, 0, 0, positive 2.5, negative 7.5, 0, negative 7.5, positive 2.5. And this and this show our max shear that we calculated. Yep. You probably did that's symmetric. What do you mean transpose?
Well, I mean, like the 2.5.
Oh, okay. That probably means that you maybe you had to transpose this times q. Anyways, like I said, I maybe wrongly feel like it's useful to see this process once by hand, trying to sort of show how some of these pieces fit together or whatever. But all that you're going to ever have to do in this class is get the eigenvalues, put the eigenvalues in the diagonals of your matrix. That's your principal stress tensor. Use those to calculate the maximum shear stress. And then that value you can use to figure out whether you're concerned about this material being deformed permanently or anything like that. Anybody have any questions? It's a lot. I mean, I guess I was sort of thinking like the main benefit of this would be kind of having it in your notes. If you ever, during this class or after this class, want to sort of mull it over how it fits together, it's there, but you don't really have to worry too much about this. Okay, let's do the quiz, and then we're done with this next time.